Welcome back to another GCSE Science Simplified deep dive. Today, we're unlocking the secrets of probably one of the most iconic charts in all of science, the periodic table. You see it on classroom walls, right? Often looks like this big, colorful grid. But how did it actually come about? We're going to unpack its story, how it was created, how it's changed, and really importantly for you, why it's structured the way it is. Understanding this will seriously help with your GCSEs.
Definitely. And what's really fascinating here is it's not just, a list. It started as a pretty simple idea and grew into this incredibly powerful tool. It helps us understand chemistry, predict new elements. It explains so much. So yeah, this deep dive should help you really get it, not just memorize bits for an exam.
Okay, let's dive in. The first big name everyone associates with the table is Dmitry Mendeleev. I mean, imagine trying to organize elements when you only know about, 50 or so? How did he even begin? It sounds chaotic.
Well, he was brilliant. Mendeleev didn't just list them randomly. He looked really closely at their properties, things like how they reacted with oxygen or hydrogen, their melting points, densities, that sort of thing. And he started noticing patterns. He saw that similar properties seemed to repeat, like periodically as he arranged the elements.
Right, hence the name periodic table. Makes sense. But here's the bit I always found amazing. He actually left gaps in his table. Why on earth would he do that? Seems unfinished.
It was incredibly bold. And that's a great question. Why leave blanks? See, he wasn't just organizing what was known. He had this confidence, this prediction that new elements would be discovered, and he predicted they would fit perfectly into those gaps. He even described what they'd be like.
He predicted their properties without knowing they existed.
Exactly. Like he described Eka aluminium. Eka means one in Sanskrit, so like one space beyond aluminium. He predicted its density, its melting point. Later, it was discovered and named gallium.
Wow.
And he did the same for Eka silicon, which turned out to be germanium.
And when they were found.
Their properties were almost exactly what he'd predicted. It was huge. It wasn't just luck. It was massive proof that his underlying system, his whole way of organizing them, was correct. It turned the table into a predictive tool, not just a list.
Okay, so Mendeleev's table was revolutionary, especially with those predictions. But it wasn't quite the table we use today, was it? He ordered elements mainly by atomic mass, right? But sometimes he had to swap pairs around, like iodine and tellurium, to make them fit the property patterns. Why did he have to do that?
That's a key point. He bumped into a problem he couldn't have known the reason for back then. Isotopes. Isotopes are atoms of the same element, but with different numbers of neutrons. So they have slightly different atomic masses. Ordering strictly by mass sometimes put an element with a slightly heavier isotope before one that should have come first based on its chemical behavior. It messed up the pattern occasionally.
Ah, okay, so the modern table fixes that. How?
It does. The modern table uses atomic number instead of atomic mass.
Right, an atomic number is just a quick refresher for everyone.
Yeah, simply the number of protons in an atom's nucleus. It's unique to each element. Hydrogen has 1 proton, helium has 2, and so on. Because the number of protons defines the element, ordering by atomic number means elements with similar chemical properties always fall into the same vertical columns, the groups. No exceptions needed.
Okay, that makes sense. It fixed those little inconsistencies. So let's look at the structure we see now. Rows and columns. What do they tell us? Let's start with the rows.
The horizontal rows are called periods, and they tell you about the electron shells. So elements in period 1 have 1 electron shell. Period 2 elements have 2 shells. Period 3 have 3, and so on down the table.
Got it.
Yeah.
More shells as you go down. And the vertical columns.
The groups.
Ah, the groups are crucial for understanding chemical reactions. Elements in the same group generally have very similar chemical properties. Why? Because they have the same number of electrons in their outermost shells.
The valence electrons.
Yeah.
Exactly, the valence electrons. And those are the ones involved in bonding and reactions. So like, look at group 1, the alkali metals. They all have 1 electron in their outer shell. And they're all super reactive because they want to lose that electron.
Right, like sodium and potassium.
And then you look at the other side, group 0, the noble gases, they have full outer shells. So they're very stable, very unreactive. Helium, neon, argon.
Okay, so periods show shells, groups show outer electrons and similar properties. That's clear. One last thing, the split between metals and nonmetals. Where do we see that on the table?
Yeah, there's a sort of zigzag line, a staircase towards the right-hand side. Generally, elements to the left of that line are metals, that's most of them, and elements to the right are nonmetals.
And the main difference in how they behave.
Well, chemically, metals tend to lose electrons easily to form positive ions. That's partly why they conduct electricity well. Nonmetals, on the other hand, tend to gain or share electrons to form negative ions or molecules, and they're usually poor conductors.
So understanding that basic metal-nonmetal division helps predict a lot, too.
Definitely. Metal reacting with a nonmetal, you can usually predict what kind of compound might form.
Brilliant. So the periodic table, it's definitely not just a random chart. It's this incredibly organized map. From Mendeleev's clever guesses and those gaps to the modern understanding based on atomic number and electron structure. It really is a scientific masterpiece and super useful for your exams.
It really is fundamental. And it makes you think, doesn't it? We understand the patterns now, but what other surprising properties or even new elements might these patterns predict that we haven't even thought of yet? The story's maybe not completely finished. Keep exploring, keep asking questions. You'll find chemistry is all around you, explained by this amazing table.